Hi, my name is Jackson Gallagher, and I'm the project lead for the Robotic Hydroponics team. We're really excited to show you our vision for the future of agriculture. My teammates will brief you on the demands of this industry, and then we'll explain how our design choices sought to meet these demands, along with some of the challenges we had to overcome along the way. And now for Patrick, Daniil, and Navier to explain how the industry works and how our robot is going to impact it.
Hello, my name is Patrick Vigeant, and for this robot, I helped with the inverse kinematics behind the movements of the robot, the actual coding that dictates the movements of the robot, and helping to design the end effector for the robot. By the year 2050, the human population is expected to grow to about 9 to 10 billion people, which is about 1 to 2 billion more people than the time of recording. With the increase in human population will also become the increase in food demand. One of the consequences of climate change is that in the future there will become more water scarcity. So the main issue for society will be how do we grow more food with less water? One of the potential solutions to this is vertical farming. Vertical farming uses less space and therefore water can be used more efficiently. In order to increase the efficiency of vertical farming, we can use robotics, which was the scope of our senior design project.
Hello, my name is Navier Lopez, and for our senior design project, I helped with the initial kinematics of the robot arm. The motivation to stay focused on this project was the chance to solve an industry problem. Any disruptions in labor in the agriculture industry could have severe repercussions. The implementation of robotics would help to reduce the demand for labor as well as the need for contact with produce. The motivation to successfully conclude this project, as well as the challenges posed by COVID, provided a topical lens that emphasized the impact that solving a problem of any scale could have.
Hello, my name is Daniil Shakov, and in this project, I was directly responsible for design requirements and assisted design choices. It is crucial that the team did not simply build a robot, but instead design a robot that directly addressed the requirements and needs of the intended industry. I leveraged my professional experience in hydroponics and vertical farming to act as intermediary for stakeholder feedback and design implementation. For instance, the demands and interactions dictated by PVC piping and growing mediums had a direct influence on the design of the end effector discussed later in the video.
And now for Alex to join Patrick in explaining how our code works to control the robot.
Hello, my name is Alexander Monrreal, and my role in the team was to create an end effector and calculate the inverse kinematics of the robot.
In an ever more technical world, dominated by computers, it is important that engineers of today are more technically literate in one or several coding languages. In order to control the robot, within the scope of this project, a code was created to calculate the joint angles needed to move the end effector of the arm to a specified position. An Arduino Uno R3 was used as the controller in this project.
To send a code to the Arduino, a sketch was created within the Arduino IDE using the C++ language. Several different iterations of the code were created to complete the task, but the team needed to find the best fit for this project. Using inverse kinematics, positions were inputted into the code to calculate angles for each servo motor. Doing so, the end effector moved to the desired position. The motors themselves were attached to an Arduino shield to simplify cable management and power supply. This shield needed its own library in order to operate the motors. An extra function was created to convert pulse width modulations into degrees that the motors can then act upon. For loops were then used to give each position its own iteration. Through each iteration, new angles were calculated for the new position, with those angles being sent to the servo motors.
This project demonstrated that even as an engineer, you may find yourself presented with unique problems that you may need to find unique methods of solving. For example, in this project, the team could have plugged all the angles into a calculator and solved for each angle by hand. Doing so would have been extremely time-consuming. Writing a code allowed for the Arduino to solve the angles in mere seconds. In industry, you may also find yourself in situations where you could solve a problem by hand, or by computer programs that require more parameters than what your problem provides. You could also write your own code more specific to the problem at hand, which therefore could save a lot of time. This knowledge would prove to be an invaluable tool within a career in industry.
Additionally, Every good code needs an interface for the customer to interact with. That's where Christine is going to step in.
My name is Christine Wilder, and I'm the Vision System and UI developer.
The UI was designed using Qt Creator and sends user inputs to the Arduino code through ports. The first mode of the UI allows the user to input any 2 coordinates for the robot arm to move from. The second mode allows the user to input a series of angles to program a path for the arm to follow. There is also a video streaming button, which allows the user to go to the video stream without typing the IP address of the camera. A wireless ESP32 cam is used for video streaming. It's attached to the end effector and waterproofed with silicone. The camera was programmed to act as a Wi-Fi hotspot using Arduino. Once connected to the hotspot, the user is able to open any browser and enter the IP address of the camera to view the video stream.
Finally, we're going to have Christian Almeda explain how the design came to fruition and how the physical choices impact the system overall.
Hi, my name is Christian Almeda, and I am the team's mechanical design and manufacturing lead for the Hydroponics Robotics project. As a mechanical design lead, I was mainly in charge of designing the robot you have seen previously, and within its design we went through various prototypes and ideas, accordingly with our consumer requirements, and finally within bi-weekly overviews with our stakeholders, we decided to create a smart, sleek, efficient, and cost-effective design, and implement each of these into a single robot. Now, various designs in today's market consist of extremely and highly expensive components and very complex parts, which mainly removes the main purpose of the consumers, which is high inexpensiveness and ease of use. This is something both us and the stakeholders mainly focused on, and with our design, we have achieved so by making an entirely 3D printable and easy to build robot. 3D printing has enabled us to quickly manufacture parts for both prototypes and final assembly, all for less than a fraction of what a current robot costs in today's market. This also enables the consumer to quickly reproduce more parts and more robots for a complete hydroponic system while including minimal and inexpensive electronics. We were also able to reduce the cost of electronics with use of an Arduino microcontroller, 4 servo motors, and a regular DC power supply. All these electronics are safely placed in a custom-designed water-resistant 3D printed casing, as the robot has to perform its functions within a high moisture and water-exposed environment. This separates us from most competitors as they mainly incorporate difficult-to-use and expensive electronics, which are also not water-safe. For our hydroponic robot, we simulate a PVC hydroponic transfer line in which plants are moved from one PVC line to the other when they grow and get bigger. This is certainly a challenge, but with careful calculations and workspace design, we were able to simulate a highly accurate transfer process as you're seeing right now. This design represents a small-scale PVC line where water is circulated and recycled back into the pipes. In the agricultural process, plants like herbs and vegetables are placed on these tubes where they're expected to grow. After a few days, they are moved to a new PVC line as their roots grow bigger and they risk entanglement, which can be deadly for the plant. Now, this is where the hydroponics robotics takes place by safely and carefully moving these plants into a wider and new growing space.